Today, I want to present how to use serverless for data science. And let's start. So first, what is actual data science process? How does it look like? Well, usually people start with gathering requirements from business, understanding your objectives. Once you understand that, you start gathering data and clean it, usually one of the hardest parts. Then you architect your model, you try different approaches, some of them fail, some of them succeed. Then you try to deploy it, some also hard stuff. And then finally you get feedback from customer, does your model work, does it not work, and so on. The issue here is that basically last three steps usually are very iterative. So you get feedback, you have to update the model, you have to deploy it, and so on. So one of the challenges is how to put your model into production as soon as possible and get early feedback. Basically, what I want you to take away from this talk is that serverless infrastructure is useful for tackling data science challenges, some architecture examples of using serverless for data science, and the use cases do and don'ts. So serverless right now is a very wide thing. As you can see, right now there is a big spectrum of how you can deploy application, starting from on-premise, meaning you own everything, functions as a service, meaning that you just control code on the highest level and you don't control anything below, or and other stuff. Specifically, usually people mean only fast as a serverless, but for data science, I want to get a more broader approach, basically from container as a service to function as a service. And let me tell you more about all of them. So let's start with functions as a service. So basically, imagine it's AWS Lambda, Google Cloud Functions, Azure Functions. Basically, you just need to put code and libraries, and everything will work. Basically, you don't need to define anything else. Container as a service is a little more complex. Basically, you will have to define some image, basically, usually Docker. And once you define it, your system by itself will scale the cluster and run your Docker container on the cluster. The main thing here is that you don't have to control the cluster itself. You don't have to SSH into your machine, although you can. And platform as a service is basically the layer which allows to control it. It's examples like AWS Step Functions or Azure Logic Apps. They kind of help to tie everything together. Because both functions as a service and containers as a service, they're completely stateless implementations. So they don't store state. And that's why we have platform as a service, which works as a storage for state. So let's start with functions as a service. To put it simply, how it works. You define Lambda configuration, on example with AWS Lambda. You define code libraries and some configuration. And once the service receives trigger, which could be API, which could be changes in your database or query, it will get your configuration and code, get a container from the pool, and put your code within container and execute the request and produce the response. And it will keep this container warm for up to 5 to 10 minutes. It could be different in different cases. And if you get another request in the next 5 minutes, you will get a lot faster execution, this is what is called cold execution and warm execution in serverless. So what can act as serverless triggers? Usually a lot of stuff. In AWS, it could be database, it could be file storage, it could be API, it could be cron job or queries or even chatbot. So some pros, cons, limits about Lambda. So it's very easy to deploy, no Docker knowledge required. Very easy to connect to other AWS infrastructure. Very scalable, you don't need to worry about that. And it's relatively cheap. There are some issues though. It can be pretty hard to debug it locally. You don't get any economy of scale. So at a large number of requests, let's say 10, 20 million requests per month, probably cluster will be more cost effective. And basically, the warm container logic, which I told you about, it's unpredictable. So there are general knowledge about how it works. There are some life hacks about it, but there is no way to control it. For example, you cannot keep cannot tell AWS to keep 10 or 20 containers warm at all of the time. And there are certain limits. Next, let's check container as a service. It's kind of serverless cluster. We have cluster here, we have servers here, but it's kind of serverless in a way that you don't have to care about servers. So basically, it's usually two things. It's either a cluster which scales completely automatically based on your job queue, or there's a service which basically makes one VM per job. So basically, AWS batch is an example of the latter, and of the former, and Fargate is example of the latter. So if we compare Lambda, Fargate, and batch together, like where can we use it? Basically, the difference is that Lambda has the fastest invocation. Fargate is in the middle, so it's like 10, 20 seconds. Batch is the slowest. But Fargate is very limited. It only works with CPUs. So in case you need GPUs or some custom instance, you will have to use batch. But you can utilize spot instances, meaning they will be a lot cheaper than your on-demand ones. But with Fargate and batch, you need to remember that although pricing is per second, the minimum billing time is 1 minute. So if your job is under 1 minute, let's say 45 seconds, you may want to work with AWS Lambda. Let's compare prices between all of them. Basically, you can see that Lambda is the most expensive one. But why people use it if it's 2 or 3 times, or even if we compare with Spot, it's 5 times more expensive. Because pricing is per 100 milliseconds. So for all small jobs, Lambda is perfect. Fargate, although it's on par with pricing with AWS batch, it actually allows you to customize your instances. So you can put more CPU and less RAM, or more RAM and less CPU. In this way, it could be more price efficient than batch. And obviously, it will start faster. And finally, batch, which is you either can use on-demand instances, which are pretty expensive, or spot instances, which is 30–40% of the on-demand price. Now let's compare GPU instances. So Lambda and Fargate don't provide GPU instances, so we will have to compare with SageMaker, which does provide it, ML instances, which are pretty expensive, but they have their advantages. The thing you need to remember is basically, if you utilize spot instances specifically for GPU, it's a way to save a lot of money, and batch allows to do that. So now let's move to platform as a service, specifically to orchestrators. So when we're speaking about serverless, it's we think that everyone understands it's microservice architecture. It's not monolith. So as a microservice, one of the issues is how you connect microservices together. There are 3 ways how you can do it. So you either use a REST API, you can use a query between microservices, or you can use orchestrator to handle the whole workflow. REST API query is usually the case when you choose when you want to save money. So it doesn't allow to trace the whole process, but you can basically have some custom logic. Orchestrator is very useful for expensive workflows where you want to have specific custom logic to handle errors, schedule, and so on. Specifically, I'm speaking about, although there are open source orchestrators, I'm speaking about cloud native orchestrators. Why is that? Basically, they have a very good integration with the services I mentioned, with both FAS and CAS. They have central monitoring, central tracing, and they scale on demand. So you also don't need to worry about that. There are 2 kinds of cloud native orchestrators. It's AWS Step Functions, and Azure Logic Apps. AWS Step Functions has a very nice integration with a lot of other AWS services, including DynamoDB and so on, and AWS Batch and Fargate and Lambda. The downside, it has static parallelization. So in case you want to branch out, you have to define 10 branches, for example. With Azure, you can define it it can be dynamic. You can, based on the process itself. And Azure has better integration with a lot of other services. For example, it could integrate with Google Spreadsheet. Specifically about AWS Step Functions, they allow not only just handle functions as a service and clusters. They allow to make a logic for error handling, even custom logic. So you can have different branch depending on the type of the error, customized number of retries, and basically have some loop logic. And you can make a scheduler, so basically wait for some process to stop or wait, basically run something every day and so on. So now that I concluded describing serverless infrastructure, now let's describe what is actually serverless approach for data science. Basically, we're using AWS Lambda for simple, short processes which we want to run in parallel. We're using AWS Batch for heavy processing which require GPU, usually. And we use AWS Fargate for long-running processing on CPUs. And we use step functions to organize the whole workflow. Let's start with first challenging task in data science is organizing data pipeline. You have multiple sources, you have multiple frameworks, libraries. You want it to be scalable because you receive a lot of data in one go, so you want it to scale. And you have combination of different types of processing. So in this way, serverless allows you to combine it. So basically, you're using AWS Lambda for parallel processing, so you try to parallelize it as much as possible. And you use cluster for heavy processing or long processing. So when would you want to use it? So basically, if you have peak loads, because it scales automatically and it will allow you to handle it, and if you have custom logic in your business logic, so you want to, for example, run some workflow every day, or you want your workflow to wait for some events, or you want to have a customizable pipeline. There is a repository which I will show demo in the end of the presentation, and I will show you how it allows to easily deploy this kind of pipeline. Next is machine learning deep learning training pipeline. So the changes here are pretty obvious. So GPU instances are expensive, and when you have your model defined, you want to check 100 sets of hyperparameters, and they're independent, so you want to check it in parallel. And you want to have sometimes semi-automatic logic. Because let's say you want to train the model, you want to see the results, you want to give some feedback to the model, and then retrain it again. Here, it's also kind of serverless can help a lot, because you can have a preprocessor, you can have hyperparameter checker, which would basically generate all sets, and based on it, it will start the whole jobs on clusters in parallel. So it can start a big spot fleet with GPU instances, process everything. Then you will have a handler which will get all the results, and you can choose the best model and save it. And you can have feedback loop in case you want to give some feedback to the workflow, or if you want to handle errors, for example. So if you, for example, want to train models on demand for some users, it could be a useful thing. And because you can, all process happens independently of each other. So you don't have to use, your workflow doesn't have to use the same cluster. If you have a peak loads, and if you want to retrain models regularly for your users. I don't know if this is not for you. So basically, if you want to make a prototype, then SageMaker is probably better because it provides a better UI, a better way to start, and it's a lot easier. Although it's more expensive, as we remember from the pricing slide. And if you have a very complex model where you need to use machines with multiple GPUs, then you will probably have to kind of define the whole cluster, dedicated cluster, where you will have parallel training on multiple machines, and you will have to use frameworks which allow to handle it. So it usually takes time, but if you have very complex model, it's the only way. So same repository, I will show demo later how to work with it. And finally, machine learning and deep learning inference pipeline. Usually, the challenges here is that, for example, you have a feature extractor in PyTorch, you have model itself in TensorFlow, well, usually vice versa. You want to kind of use some framework to pre-process images like OpenCV and so on. So you have this zoo of different frameworks, and you want them all to work together. You have different versions of the model, and you want to be able to compare them. And you want it to be scalable, because everyone wants everything to be scalable. And finally, you may want to have some custom logic for choosing the result. Basically, just one about custom logic. Let's say you have model A and model B, and you have new model, and you want to basically if the results of new model are too different from old model, you want to use, for example, still old model, basically, to have this kind of like canary deployment, but in softer way. So that's how usually inference architecture looks like, which is like just API, deep learning API. You have root 53, you have load balancer, you have cluster. Within cluster, you have the scaling group and spot instances. And the ECR for keeping Docker container. And it's very basic. It's like just simplest architecture. Same architecture, same application, just using serverless, just API gateway, Lambda, and model on S3. That's all. You can use not only API gateway, you can actually use something like SQS, like queue, if you have a lot of tasks and you want to batch your jobs. And you can use SQS together with Lambda to connect SQS to step functions. Basically, why would you want to use step functions? Is that if you want to have like custom logic where you have multiple frameworks, you want to run TensorFlow on Lambda to extract features, run 2 models on PyTorch, and compare the results after that, and give then some result back to the user, then step functions allow you to do that, and allow you to basically see the logs and trace everything. So how import works like if you have inference on serverless? Usually it means that you have to keep your model on S3 bucket, and you have to download it every time. It doesn't sound optimal, and it's not optimal, but you only have to do it for cold invocation. For warm invocations, you don't have to do that. So let me give you an example of pricing, like when we run inference on AWS Lambda. So Inception v3, which is like a model for image classification. So if we put RAM with Lambda, RAM scales together with CPU. So we have 3 GB RAM, and it will mean that we have like 2.8 seconds for cold invocation, 0.8 seconds for warm invocation. As you can see, not only cold and warm invocations like influence time, but it also influences your cost. So you want to optimize to have as much warm invocations as possible, because like if you have only cold invocation, it could be pretty expensive. Although like for pet projects or for startups, having like 10K invocations per $1 may be okay. But if you are able to utilize warm invocation as much as possible, you can have like 30K invocations for $1. One thing you also need to keep in mind, choosing the biggest RAM and the biggest CPU may not be the most optimal way. Although you get the best speed, you also will have more expensive lambdas. So it's something which you need to balance and choose. What are some optimizations which you can do when you run inference on serverless? So first, try to optimize and have as much as warm invocations as possible. Try to store some part of the model with the libraries, so you don't have to download a lot from S3. If you download from S3, download it in parallel. S3 allows to do that. And basically, one of the changes that 3 GB RAM has 2 virtual CPUs. So you have actually multiple threads on Lambda. And one even more complex life hack which you can do is if you can kind of cut your model and separate it, you can basically chain 2 lambdas together, and so you don't have to download the model, but you will need to pass intermediate features from one lambda to another. But it will help because basically all your cold invocations become warm. And basically the best way is to batch your workload, so you don't process like 1 image, you process 10, 20 images. So how do you know like if this kind of inference works for you? So if you have pet project and you want to deploy it, it's good because basically Lambda is a freemium service on AWS, so you get like 400,000 like gigabyte seconds per month, which is a lot. If you have a startup and you want to make like, you don't want to hire DevOps and you want to make like the simplest deployment possible. And if you have simple model and you don't want to make a custom cluster which you need to support, Or finally, if you have very high peak loads. So you're basically, your processing happens completely on demand. And when it doesn't work. The whole thing, like, it doesn't works really well with real time. Well, depending what you think, like what you define as real time, but you basically saw like it's very hard to make it work like in 200 milliseconds or something like this. So if you want your model to work as fast as possible, then you need to go, use cluster. You require a lot of data or processing power, you will have to use cluster. And if you need to handle more than 10 million requests per month, you need to use cluster because it will be a lot cheaper. Two projects, basically, project number one is image classification, which allows to basically classify the image. You can see the link to repository and the link to the tutorial, where you can basically run it within your LBS. And example with image captioning, where basically model describes what's happening on the image. Basically, the main idea here is that it's very easy. There are a lot of pre-trained models out there, so you can just pick pre-trained model, put it inside Lambda, and you will get deep learning like service, and your startup can move to .ai domain. Basically, there are two main repositories here. So one with packages for Lambda, one is packages with Google Cloud Functions. Basically, it has deep learning packages, even like Beta TensorFlow 2.0. It has LightGBM, H2O if you need something for machine learning. It has a lot of processing libraries and Spatie for natural language processing if you need it. So here's the link to the presentation. Let me check. Yeah, I have some time for the demos. OK. In my demos, I'm using a serverless framework, which allows to deploy Lambdas together with step functions and a lot of AWS infrastructure. I deployed this earlier today because like the problem with AWS batch is it takes something like 5 minutes to deploy. But you can basically, let me show you. Basically, as you can see, it produces URL, which you can use. And basically, here, let me basically, you can just post it. And let's send multiple requests. And OK. So here is how step functions look like. You can see that you have dashboard that you can basically see how many things you have running. You can then get inside and look at each one of them and see like how the process goes. So right now it's on batch step. Next, let's go to AWS batch. So you can see that we have 11 runnable jobs. And right now, it will try to start cluster. Basically, here we are in EC2 dashboard. As you can see, it created a request to start a spot fleet. I will show you code later, but basically, it starts everything by itself. And once it will start, like you can see that it tries to start 11 machines to process jobs, one job at machine. And it will try to do it, but it usually takes some time with batch. Doubly so if you use GPU instances. But the good thing is basically, if you can, it also gives you a way to have log for each machine. So you can trace like what's happened on each machine with each job. So basically, this is a centralized log for all AWS batch. Here is the repository, which basically has the code and configuration. Basically, let me show. So it contains two things: Dockerfile and exec, which is like Python file. So here you can see it's a very simple NIST, but like fashion NIST example. And the Dockerfile, basically, AWS provides instances which you can use with GPU. Basically, the only thing you need to run is you need to build a Dockerfile, you need to push it to UCR. Once you have link to UCR image, you can get here. Basically, here the main part is serverless YAML. Basically, it's a configuration file for serverless framework. Here you define basically, or you define lambdas together with batch and everything. Here, basically, you define lambdas. Here you define step function. Basically, you define like the tree, execution tree. And for each node, you can define node to be, for example, task. Or it could be, here it's lambda. And or it would be task which would run on AWS batch. And you can customize command which will be executed here. Basically, it means that you can put here a custom command based on the response from previous step. And you can put everything in parallel. And the parallel execution will stop as soon as all nodes are either completed or failed. So basically, you define your execution tree here. And here in resources, you just need to put your image URL, which will be produced by ECR. And basically, the last part of the resources is just like all things you need to deploy if you want to use AWS batch, like subnets and so on, but you don't need to worry about it. So basically, because it will be deployed together with this configuration. You can customize your instance types. You can even customize your bit percentage. I put 100 because basically that's the usual thing, but you can put 50% if you only want it to run like if it's only half of on-demand price or something like this. So basically, it's very customizable and allows you to. You can either like remove spot and use EC2 instances if you don't need, because with spot instances, and there is a problem. There is. Let's check with step function execution. OK, as you can see, some of them already succeeded. Some of them are still running. But the issue here, and let's see how. Yeah, as you can see, it started only 2 machines out of 11. And as you can see on the history, it says that it cannot implement it because right now, spots are exhausted on US East 1. 2 main lessons to learn. First, don't use US East 1. Lesson number 2, basically make sure that basically it's something which you could expect that could happen with spot instances. So for some workflows, you may want to use EC2 instances instead, although it will be pricey, but it will start a lot faster. And also you need to take into account sometimes with spot instances, it can suddenly finish and fail, and your workflow has to handle it. OK, basically, once basically there is a README file which you can read and more about how to deploy it. But basically, once you have everything defined with configuration file, you just need to run like serverless deploy. And that's all. And now let's look more at the inference. Basically, here is you can see there is a GitHub project which has all these libraries which I mentioned. Specifically, here you can see TensorFlow example. And you can see the code and libraries which you can use. And here, let's look at the Lambda with deployed inception tree model. So now it will be a cold start. So it tries to recognize the image of Panda. OK, so the cold start, you can see it was even 4.5 seconds, basically. Now let's basically try one more time. It will be cold start. You can see 700 milliseconds, like a lot faster. So, and basically, that's why you need to kind of try to utilize warm invocations as much as possible. Or try to put your model inside the libraries or other life hacks. OK, that's all. Both demos worked almost correctly, so that's a good thing. And thank you very much. And if you have any questions, I will be happy to answer them.
Any questions? All right.
When you're packaging your data science models and libraries, some of those libraries are quite big. Have you bumped into the file size limit for Lambda? And how do you get around that?
Good question. So there are two things. First of all, usually AWS Lambda says that it has like 50 megabyte limit on the zipped package. It only if you upload your zip directly from S3, there is no limit like this. So it's just the limit of 250 megabytes unzipped package, which is not a lot, but still workable. But then it's kind of the art of packaging like TensorFlow, and that's why basically that's why GitHub repository exists. Let me show you. Basically, there is a shell script with build pack, which basically you can run locally to gather all the pack. Basically, it installs libraries, and it deletes everything which you don't need. Basically, PIC files, it compresses shared libraries, it removes like libraries which won't be invocated or already exist on AWS Lambda, all of this stuff. And then it basically can be fit inside the AWS Lambda. So basically, you can use this shell script with your local Docker to do that.
All right. Well, thank you very much.
Thank you.